Hi, welcome to Project Geospatial. I'm Adam Simmons, and here with me today is Chul Gwon with Analytic Folk. And in this segment, we're going to talk about machine learning, what it is, and how it applies to the geospatial world. Just kind of an introduction to that topic. Chul, how about you introduce yourself, your experience, and how you got where you are right now, and then we can start talking about machine learning.
Sure. And so I graduated from Ohio State. Back in the day, I did experimental particle physics. I decided after that I didn't really want to do experimental particle physics, and so kind of went to software development, various things like that. Got caught up in the sorry about that. Got caught up a little bit in kind of the big data phase, the big data analytics and whatnot, and then machine learning was kind of getting hot back. When I first saw it, it was 2014, and so just kind of like that captured my interest in the various things you could do, and kind of brings us to today of the kind of things that I'm doing now. But it's kind of a brief history of how I got where I am now.
And you said you had a Ph.D. and specifically
I did so I was doing particle physics at the time. So
okay, so how much has from an education standpoint? Because I like talking to folks who want to. I like explain to folks what it takes to kind of get into the field, and it didn't require you to get into particle physics first to get into machine learning. Obviously, how did you branch into machine learning from particle physics?
It's a good question. I mean, honestly, some people...
And this is your personal story, obviously, but we have a lot of folks who listen to the show who are getting involved with their careers for starting out and wondering what path to take from an education standpoint.
Honestly, it's because I get asked this. I've been asked this during interviews. It's like, do you think a PhD is really... I mean, do you think your abilities are enhanced because you have a PhD? Honestly, I wouldn't say that. There's so many packages out there right now that make it relatively straightforward to test, just kick the tires and test this stuff out. So really, if you just have the interest, I mean, some mathematical background, obviously, to understand it, some coding experience like that, but I mean, nothing near what you would get with a PhD and whatnot. I would say just, even a strong undergrad with a decent math and like programming background can right away get started with some of this stuff and kind of get the ball rolling.
Yeah, no. So taking this to the machine learning part, can you explain to us what machine learning is, and from a very kind of basic form, and then once again, let's get into how it involves the geospatial community.
Sure. No. And so machine learning, a colleague at UMBC once said, that there's artificial intelligence, and then artificial intelligence is more like just doing anything to make a computer do something smart, something that seems smart. I mean, that could be as simple as like a lookup table, right? Like a bunch of if-then clauses, if-then else's to try to make a decision on what to do. Machine learning specifically is getting the machine to, through experience, whether it's doing a repetitive pattern or seeing a repetitive pattern and identifying it over and over. And so that's really kind of what I think differentiates machine learning specifically from artificial intelligence. What I spend most of my time is something called deep learning. Deep learning uses something called neural networks in order to do things like machine learning. I mean, machine learning, there's hundreds, thousands of algorithms out there. You can do various clustering, and you can do just kind of statistical analyses to get these results. But the deep learning really kind of takes advantage of these neural nets, which has really kind of come in stride since it's kind of, come and gone for several decades now, but I don't know, I'd almost argue 2012, 2013 is really when it hit its stride the most.
So what does it take to teach a machine how to do something from an automated approach or pick up something? Talk to me about that.
Sure. And so there's a couple different ways.
And how about this too, just for the sake of the industry that we work in, geospatial, let's start driving that, talk to me about what it takes towards that industry, because obviously machine learning could apply to a bunch of different things. And I think it will help the audience if we focus a little bit more.
Sure. Okay. So when you're dealing with machine learning, there's a couple different ways, a couple main different ways. And the way that most people do it is something called supervised learning. The way you do supervised learning is essentially, let's say you're trying to identify a particular object of interest in an image. Well, what you do is you'd find a bunch of examples of that type of object. You'd label it or annotate it, and you'd essentially feed all of these images with the labels into one of these neural networks and allow it to figure out, okay, this type of edge or this type of color scheme or something is typically important with the object of interest that they've labeled. And after seeing enough of these examples, it starts to figure out, okay, if I see this type of shape with this type of color or this type of texture to it, then I know it's going to be object X. And so that process is called supervised learning. That's the most traditional way. There are other ways you can do it. There's ways that you wouldn't necessarily need, like label data. It's called unsupervised. And then there's also the entire field that's I guess somewhat different, called reinforcement learning. That's been popular with like what you've seen with like Go and figuring out how to play Dota 2 and things like that, the video games. But for the geospatial world, it really does. I mean, the biggest thing people do is still supervised learning. Again, a couple different unsupervised techniques that people are experimenting with, but most people traditionally still stick with supervised when they're starting out.
So how does this all connect to, I've heard the terminology a lot over the last couple of years when folks use assisted machine learning too, that terminology. So at what point do you assist the machine instead of relying on it completely, or is that just a different philosophy with machine learning?
It's really a different philosophy. I mean, personally, I've always thought, it should be used more as kind of an augmentation tool, right? I mean, one of the biggest problems is, the machines might be susceptible. It might think that, that this is definitely a car, and it's really not a car; it's a bicycle. But given that maybe the size is too small, or maybe the aspect ratio is different or whatnot, it might get confused. And so, definitely, it's like it seems like it's much more effective if you can kind of like keep the human interacting with it somehow. I mean, one of the most powerful things you can do is a lot of times it's just there's just so much data, right? And if you could completely obliterate like the ones that you know for sure don't have anything interesting in it, and hey, here's the last few hundred samples which might have some interesting things in it, right? Having them go through like a few hundred, or I mean even like 1,000 or something is much better than if they have to try to go through millions of images trying to find something relevant or whatnot.
Yeah, no, that makes sense. But what does it take to train a machine? So you need a lot of sample data. Is that correct?
Right.
So how long does it take normally to do this? And there's a lot of different philosophies on that too, right?
No, definitely. And so it really depends on what you're trying to look for. I mean, so a lot of times there are models that have been built commercially, right? That can then, the feature space will be similar. I mean, the types of features you're looking for will be similar. And so for something like that, you wouldn't necessarily need as much data. I mean, if you're looking for, if you're using a terrestrial-based camera and you're looking for cars, there are plenty of models out there that can find cars pretty well. And so if you want things to detect faces, or if you want things to detect like just people walking around, with a stationary camera, stuff like that's relatively straightforward. The problem is there are some models out there that have been designed for geospatial, but it's significantly less because everyone can walk around with their iPhone, take the movies and essentially label them up and release these models. Not everyone necessarily has access to like geospatial data or satellite data or things like that in order to train these models. Now, there's lots of competitions that have come out like XView and whatnot, where they've released data and people have trained models and released some of them. But these are much more scarce than just kind of like the common everyday videos that people see.
So it's so emerging that there's not even a whole lot of open source tools and resources that you can leverage too, right?
Yeah, I mean, the tools themselves are very similar. It's just the pre-training of the models. I mean, depending on, the type of things that you're looking at, it could take, thousands of images, it could take tens, or it could take, millions of images to really make really strong models. And so, I mean, I think that's kind of a little bit where the disparity comes in. And also, the features that you see in satellite data aren't really the same as the ones you see in terrestrial cameras. And so then the effort to train a model that's effective for seeing like smaller objects of interest and things like that become a bit more tricky.
What would you say the biggest challenges to getting machine learning working in the industry are?
Data.
Just getting the data?
Yeah, I mean, that's always been, I mean, so I said things started kind of turning the corner in like 2012. That's when these neural nets finally got ported to GPUs. I mean, I think it was starting to happen even earlier than that, but 2012 is when someone from University of Toronto won a big competition called ImageNet. Essentially blew away all the competitors by using this neural net that he had ported to his GPU, and suddenly it's like, oh, everyone realized you can use these NVIDIA cards and whatnot to boost the compute necessary. And so definitely think the GPUs were one. But the second thing were the data sets. I mean, you look nowadays, and there are tons of public data sets. There's, the ImageNet data set that lots of folks have used. Microsoft released their Common Objects with Context, the COCO data set. That was really big for object detection, things like that. Open images is obnoxiously big. I mean, so the data sets themselves, as far as like ground-based, terrestrial images, everyday images, those are huge. And I feel like if we had labeled data sets similarly with geospatial data, then you'd definitely be able to make huge leaps and bounds as far as capabilities.
Awesome. No, appreciate it. So next question, complete opposite from the one I just asked you, is from what you've seen in the industry from different projects, what has been the most exciting or surprising to you from an innovation standpoint in the last couple of years from a machine learning standpoint?
So
what was kind of like blown your mind was like, whoa, okay, this is taking it to a new level for us, and especially yourself working and trying to do move this technology forward.
No, I mean, it seems like there's always lots of things that kind of, I mean, that it depends. There's plenty of things I think to get excited about. It's continually developed. Algorithms continually are developed, new algorithms, better performing algorithms, fine tuning the ones that exist. I mean, one of the ones that I personally, I was reading about that I thought was fascinating was a project with Maxar and Facebook, actually, where they actually used a technique called weakly supervised learning. So with that, essentially what they were able to do is they were able to generate a roads network using OpenStreetMap, using what they call weak supervision. The way that weak supervision works is a lot of times, I mean, especially with the data sets I've used and whatnot, I mean, if you have smaller data sets, like a few thousand, you really want the annotation to be very clean. And so what that means is, if you have an image and it has a cat and a dog in it, you want to make sure the labels, if the cat and dog are both one of your labels, you want to make sure they're both there. And you want to make sure that someone didn't accidentally label it as, a lion or something when there's no lion, it's really a cat. When you have like mislabels or missing labels, it's called noisy data. And so what weak supervision says is, if you have enough data, like millions and millions of images, even if it's somewhat noisy, you can still train up decent to strong classifiers against it. So what they did is they had tons of noisy data, which they obtained from OpenStreetMaps. But using this, because they just had the sheer amount of it, they were actually able to generate a very strong, model from that. And so, I mean, I think stuff like that kind of breaks away from the traditional, we really need clean data, we need super experts to label everything. And it's turned into, even, okay, if we have noisy data, as long as we have like tons of it, we can still actually produce useful stuff. So things like that, I think I find fascinating. I mean, there's other things. Lots of people worry about like adversarial attacks. Adversarial attacks is, if you have a common image that people see is they see an image of a panda. And if you take the image of the panda and you take like, another image that a classifier thing is just it's not random noise, it's targeted noise. But you can add a little bit of noise to where a human will look at the result and still see panda, whereas these neural networks will say, oh, that's now a gibbon, or that's like a boat, or a car or something. And so things like that are called adversarial attacks. And so there's been a lot of work around that as well to try to resolve, okay, well, how are we going to get around these attacks and things like that. A lot of that, yeah, I mean, that's also led to, adversarial attacks have also led to, well, how to defend it. So some of the things that are kind of interesting are what some of the things that people are coming up with, how to defend it. Some people artificially introduce noise. Some people train against it and things like that. So, I mean, that's quite an interesting area as well. And other thing is trying to generate your own images, right? The deep fakes and whatnot. I mean,
these are kind of gets into your more simulated data.
Yeah, and so there's an entire field which is pretty exciting called generative adversarial networks, where people actually will try to generate faces or generate images. And so still a growing field and still trying to, I mean, it's still very far from generating things the size that you typically get with geospatial, the number of pixels that you usually get with geospatial data, but still it's kind of something that's continually developing. I mean, the resolutions are getting bigger and whatnot, and hopefully, soon you'll be able to, theoretically generate these huge image chips and whatnot to develop training data that you could then theoretically train against.
Awesome. I know you have an example of imagery on the side of how it's used. I'm questioning if we should get into that now or if we should move that into another segment if you want to talk about more detailed imagery-based machine learning in a future discussion.
Sure. Sorry, go ahead.
Yeah, go ahead. Either way, I also think it would be worth understanding, kind of going back to your experience at the same time. If you were to recommend certain classes or a career path towards folks who are wanting to dive into machine learning, what path? How do you recommend their academic path move? And that's getting slightly off topic of what is machine learning, but how do you study it?
So there's a couple different things you can do. A lot of people actually, they want to take all the coursework. They kind of want to understand the theory behind it and all. And all that's good before touching it. And I mean, don't get me wrong. It's good to try to understand like the underlying theory, the underlying algorithms behind it. One of the classes that I took, when I was certainly getting started, was Andrew Ng from Stanford, who runs Coursera, also runs DeepLearning.ai, offers a set of courses that explains this stuff extremely well, and I've appreciated that. One of the other ones that I did on the side was there's a online Stanford course that's also offered there called CS231N, which goes much more into kind of the theory underneath it, developing stuff from scratch and whatnot, seeing how things are built, doing forward backward passes for these neural networks and understanding it. But for people who just kind of like want to get started, like one of the really good websites out there is something called fast.ai by Jeremy Howard. And honestly, his approach, and I actually appreciate this approach, is like there's so many libraries out there to where you can just run a neural net without really understanding it. Right? You can build a simple classifier to tell you the difference between an apple and an orange, like without much effort, because there's so many libraries. In fact, he has his fast AI libraries, which will kind of streamline this process. And the nice thing about it is you can see how it works, and then you can start to explore and you can dig into it, going, okay, why is it really doing this? What if I remove this layer? What if I use this option instead? So you can actually, it's combining kind of hands-on as you're doing other stuff in parallel to try to figure out, okay, now what's really happening underneath, right? Okay, now.
So it lets you play around with the data and the possibilities at the same time.
Exactly, and I think that's the approach I think a lot of people should take. I mean, even with programming, I mean, you could read all the theory books in the world before you touch a line of code, or you can try to code something or borrow a code from someone else, tinker with it, mess with it, kind of make a couple changes here and there and say, oh, this is what's happening. And then, as you're kind of messing with it, you can learn more and more about it. And so I definitely am, especially with machine learning, a bit more of an advocate of, get your hands dirty, kind of kick the tires. It doesn't take much effort to do that. And then as you're messing with it more and more, as your problems become more specialized, start to look into it, going, okay, why is this happening? Let me look at this and see if I can figure it out.
No, I appreciate the insight. And this is going to be my last question because we're running out of time with you for this first segment. And hopefully it's not a loaded question, but I talk to a lot of folks, and it's easy to describe, but often folks I think get confused because you use synonymously with the terms machine learning and AI. Can you explain the differences between the two?
Yeah, and so that's what sometimes it almost feels like this is a question you ask 10 different people, you might get 10 different answers. But again, I alluded to this a little bit in the beginning. Like AI is, I would argue AI kind of even, is what kind of came first. AI is really trying to get a machine to do something that someone would consider smart. And so that's why I meant going like lookup tables back in the day and things like that. Rule-based stuff where, you have a list of rules that if the machine follows, then it'll do something, right? It's not really learning at that time. It's not really learning because you've kind of programmatically told it what to do and what to look for. But after that, it can automatically try to do something repetitive that has a bunch of rules and whatnot. So so AI I would say is a much larger field that includes this kind of stuff. Machine learning on the other hand really is trying to get the machine to figure something out, showing it a bunch of examples. When I'm showing it a bunch of examples of cats, trying to teach it to learn cats, I'm not explicitly saying, look for the ears, look for two eyes, look for a nose and whiskers, and that's a cat. All I'm doing is I'm showing it a bunch of pictures, and it's in turn figuring out, okay, these set of features, when they go together, means it's a cat. And so I think that's the real big difference. I think machine learning is definitely a subset of an overarching, artificial intelligence trying to get the machine to do anything smart. And so that's kind of where I would personally not draw the line, but kind of like somewhat differentiate between AI and machine learning.
No, I appreciate the clarification. And once again, we're running out of time, but we appreciate your time, Chul, explaining machine learning, the basics of it. What is it? And Chul is with, once again, Analytic Folk, and we will have your contact information in the episode notes. We appreciate everybody for joining us for Project Geospatial. If you want to contribute and support the show, you can go to anchor.fm /Project Geo. And we hope to have you on another segment or two to go into more details about some of the specifically in the geospatial industry, maybe some of the more open discussions around what methodologies to take, and maybe some examples of imagery down the road, and just to have some of those discussions with you down the road, Chul, if you're willing. So
sure, sounds good.
But appreciate your time, and once again, thanks for joining us, and thanks for listening, everybody. Thanks.
Yeah. Thanks for having me, Adam.